Let's learn about the building blocks of FEA models, elements. Hi, I'm Dr. Iman and welcome to section 3 of the FEA Done Right series here at MechCADemy. Elements are much more than shapes that fill your model geometry. They define how the software represents the physics. For example, which degrees of freedom are included and what assumptions are made about how your structure deforms. When selecting an element, there are a few core considerations you must pay close attention to. First, the physics of the problem. Are you modeling tension, bending, torsion, or a combination of these effects? For example, cables can only carry axial loads, while beams and shells are designed to represent bending and twisting. If you choose an element that cannot model the physics correctly, no amount of mesh refinement will fix the error. Second, the required degree of freedom. Each element comes with a specific set of nodal degree of freedoms, translations, rotations, temperature, or a combination of those. For the sake of brevity, here I'm only considering structural problems though. Rod and bar elements usually have only translational degrees of freedom, while beam and shell elements add rotational components to account for curvature and out-of-plane deformation. If you leave out necessary degrees of freedom, your results will be incomplete. But if you include unnecessary degrees of freedom, you increase computational costs without adding value. Third, the geometry and scale of the part. If one dimension is much larger or smaller than the others, you can often simplify the model using one-dimensional or two-dimensional elements. For example, rods for slender members or plain stress elements for thin sheets. But when all dimensions are comparable, you typically need 3D solid elements. In this section, we'll cover the main categories of elements. 1D elements for beams, rods, cables, and pipes. 2D elements such as plane stress, plane strain, axisymmetric, and shells, and 3D solid elements including tetrahedral, hexahedral, and solid shell elements. We also cover some special elements like mass, inertia, springs, contacts, and rigid connections. As we go through them, keep this in mind. The most effective FEA models strike a balance between the physics you need to capture, the total degrees of freedom, and the geometry you have. Making smart choices here lays the foundation for accurate and efficient simulation. Let's start with 1D elements. Geometrical 1D elements are defined along a single axis. Depending on their formulation, they can carry axial forces, bending moments, and torsion. For all one-dimensional elements, the cross-sectional properties are always provided as input. Now, an important clarification. When we say 1D or one-dimensional, we are referring only to the geometry of the element, not to its degrees of freedom. For example, an element may lie along the x direction, but each node of that element can still have 3 translational degrees of freedom in x, y, and z directions. So geometry and degrees of freedoms are not the same thing. Let's walk through the main types of one-dimensional elements. A quick note before we begin. My primary reference here is ANSYS software, but these concepts apply across almost all FEA software. Once you understand the fundamentals, you can switch platforms with confidence. Let's start with rod or bar elements. These elements carry axial loads only. They are commonly used for tie rods, struts, and truss members. Each node has 3 translational degrees of freedom, U, V, and W. From now on, U is the translation in X, V is the translation in Y, and W is the translation in Z axis. In ANSYS, this is typically link 180 element. Next are beam elements. Beams are more versatile. They can carry bending, torsion, and shear. Each node has 6 degrees of freedom, 3 translations, and 3 rotations. There are 2 main beam formulations. Euler-Bernoulli beams, which are suitable for slender beams with a length-to-height ratio greater than 20, and Timoshenko beams, which are recommended for short or thick beams, layered materials, or cases where shear deformation is significant. These formulations come directly from theory of elasticity. In other words, the element behavior is governed by the mechanics of material. Euler-Bernoulli beam theory is typically covered in introductory mechanics of material, but Timoshenko beam theory usually appears in advanced mechanics of material or graduate level elasticity courses. In ANSYS, beam 188 element is commonly used and its settings allow you to switch between these formulations. Next are cable elements. Cables are designed for axial tension only. They cannot resist compression or bending. Because of this behavior, cable elements almost always require a non-linear analysis, especially when large deflections are expected. In many cases, you must include a pretension to stabilize the cable in its initial configuration. In ANSYS, this is typically modeled using link-10 element. Finally, we have pipe elements. Pipe elements are similar to beams. They can carry axial, bending, and torsional loads. However, they are specialized for circular cross-sections and can also include internal pressure loads as input. Like beam elements, they have 6 degrees of freedom per node. In ANSYS, a typical example is pipe 288. So again, remember, when selecting a one-dimensional element or any other element, you should always ask, what loads does the element need to carry? What degrees of freedom are required? And are there any special nonlinear effects such as large deflections or pretension that must be considered? Answering these questions correctly ensure that your model captures the right physics without unnecessary complexity. Now, let's switch to 2D elements. Geometrical 2D elements are used when two geometric directions are explicitly meshed, and the third dimension is entered as an input property, like thickness. First, plane stress elements. These have 2 translational degrees of freedom per node, U and V. They are used for thin sheets and coatings, where thickness is much less than the in-plane dimensions, and all out-of-plane stresses are assumed to be 0. Here, I assume all out-of-plane stresses have z-index. To use plane stress, the loads also need to stay in plane. Any out-of-plane load negates the plane stress assumptions. Second, plane strain elements. These also have U and V as degrees of freedom. They are used for long or thick bodies, such as dams, tunnels, or long extrusions. Here, all out-of-plane strains are assumed to be 0. Third, axisymmetric elements. These have UR and UZ degrees of freedom per node if torsion is not selected. With torsion, you will have an additional rotational degree of freedom. Due to axisymmetric nature of these elements, polar coordinates are used. These elements are used for bodies of revolution modeled in the RZ plane, like pressure vessels, disks, and nozzles. Note that in ANSYS, plane 182 and plane 183 elements can be used for plane stress, plane strain, and axisymmetric modeling. But you must set the correct option in the element definition. Having the right assumptions selected is extremely important because the wrong assumptions will lead to completely incorrect results. This is one of the sanity checks you need to perform when you use a 2D model. Finally, for 2-dimensional elements, let's talk about shell elements. Shell elements have 6 degrees of freedom per node, translations, U, V, W, and rotations, theta x, theta y, and theta z. Shells are technically 3D elements, but are considered 2D because they mesh surface with a defined thickness. In ANSYS, shell 181 and 281 are typical shell elements. For shells, you can choose whether the midplane, top, or bottom faces represent the geometry. They can model both in plane, that is called membrane behavior, and out of plane behavior. A special attention is needed when surface bodies meshed with shell elements are in contact with other parts. We will cover this in future sections. Next, we cover 3D elements. 3D elements are used when all 3 geometric dimensions are comparable and must be meshed in full. The degrees of freedom per node are only U, V, and W, just translations, no rotation. First, we have tetrahedral, or in short is called TET elements. They can fit complex geometries easily, but often require a finer mesh to achieve a good accuracy. Then we have hexahedral, or in short, they are called hex elements. They are also called brick elements. These elements are generally preferred over tetrahedral elements because they offer better accuracy and are more tolerant to distortion. We also have less common pentahedral elements that are wedges or pyramids. These elements are mainly used as transitional elements between hex and tet regions and are not typically used alone. In ANSYS, solid 185 and solid 186 are typical 3D elements. Finally, for 3D elements, we have solid shell elements that are designed for thin to moderately thick 3D structures. But they only have 3 degrees of freedom per node. They have full 3D thickness representation, but often use only one element through the thickness. This formulation accurately captures bending through integration points. This might sound confusing at this point, but we will make this clearer soon. For now, let me just tell you that integration is a very important procedure in FEA, and it plays a key role in how these elements work. In ANSYS, for solid shell elements, we typically use SOLSH 190 element. So far, we have covered the most common elements in FEA. Now, let's talk about less commonly used ones. They don't show up as often, but in the right situation, they can be incredibly useful and powerful. These elements don't have their own continuum geometry, but play critical roles in FEA models. First, mass and inertia elements. These are lumped properties attached to a node. They don't contribute stiffness or volume, but represent inertia in dynamic simulations and modal analysis. Next, MPCs, rigid links, load spiders, and joints. These help you define relationships between nodes. MPC stands for multi-point constraints. They enforce algebraic constraints between degree of freedom of different nodes. A special case of MPCs is a rigid link that forces one node to follow a master node exactly, or in another term, rigidly. Load spiders distribute forces without adding a stiffness. Joints, like revolute or universal, allow you to free only specific degrees of freedom, of course, based on the physics of the problem. Next, contact elements simulate how bodies interact under normal and tangential loads. They can model friction, separation, sliding, and sticking. We'll look at these in detail later because contact modeling has its own complexities. Finally, springs and dampers let you define a stiffness and damping between nodes. They can be translational or rotational, useful for modeling flexible joints, suspension systems, and vibration isolation. Note that unlike solids or shells, these elements don't define their own volume of material. Instead, they act as connectors, constraints, or special interactions applied to surfaces or nodes of your existing mesh. Therefore, each one has their own set of inputs and settings. Now, I know that many of you are already familiar with commonly used element types in FEA, such as beam elements, 2D shell elements, and 3D solid elements. You've likely used these in many of your projects, but some of the other elements we just covered are less commonly used, especially by students. So I thought it would be helpful to walk you through a few examples that show how these elements are applied in real-world simulations. Let's start with the first example, which involves a joint element. In this model, 2 parts meshed with 3D elements are connected via a revolute joint to simulate constrained rotational motion. If you look at the deformation results, you can see the connected part rotating around the joint axis. This highlights how joint elements can effectively represent rotational degrees of freedom between the parts, even if nodes don't have rotational degree of freedom. In the next example, we have a remote displacement applied in a gear and rack system. A small rotation, just 1 degree, is applied to the gear using a remote joint that's rigidly connected to the gear's inner surface. This causes the gear to push the rack to the left, creating a stress impulse. This kind of setup is very similar to what's known as an RBE2 element in software like Nastran or Abacus. An RBE2 element creates a rigid connection between a master node and a set of dependent nodes, transmitting both translation and rotation without any flexibility, essentially enforcing rigid body motion. So the remote point and its rigid coupling in this model serve a similar purpose. They ensure that motion applied to the point is fully transferred to the connected geometry, just like an RBE2 element. Another good example is the point mass used in the cryomodule particle accelerator cavity model shown here. In the actual assembly, there is a two-phase cooling line attached to the cavity, but instead of modeling the full geometry of the pipe network, which would make the model unnecessarily complex, my student replaced it with a point mass. Next, let's look at the spring elements used here to represent the axial stiffness of a mechanical tuner that adjusts the resonant frequency of the same cryomodule cavity. In this case, two springs simulate the tuner's force displacement response. These examples show how specialized elements like joints, remote displacement, springs, and point masses can simplify your models and reduce simulation time, all while capturing the key physical behavior of the system. Okay, we are done with section 3 of FEA Done Right series at MechCADemy. With a clear picture of how different elements behave and what they're designed for, let's now step into the theoretical world of 2D elements in section 4 of the FEA Done Right series at MechCADemy. I'll see you in the next section.